Everybody, thanks for coming during your lunch break or whatever you do at around 12 o'clock. Thank you for coming. Thanks to Blender Conference for giving me 50 minutes to talk to you guys about the theory of gravity and making renders of black holes in Blender. But before we get all too serious, let's imagine we are on an interstellar journey. Let's say you have come into some money, you have bought yourself a beautiful galactic cruiser to do this one thing that you always wanted to do, namely go to a black hole, see what it looks like. So you jump on your galactic cruiser and you have picked out the perfect system to go to. So in the middle, with the dotted circle, is the black hole. And this is a very special system because it has 4 moon-like objects around it. So a red one at that side, a gray one at that side, a yellow one, and a blue one. But you're not so good at intergalactic travel yet. You brake too hard, you end up on a trajectory right into the black hole. Well, this is quite bad news, but you're an optimistic person, you make the best out of this, and you decide to make some pictures and send them back home to your mother, to your family, to your friends. So this is very noble of you, it's all for science. So you get your GoPro, you put it on your head, and you start taking some images. Imagine you're getting very close to the black hole. So the black hole is right below you, and you take a picture downwards. And then this amazing picture comes out. It's completely black. Many of you have probably heard about black holes before, and it's this thing that even light cannot escape from when it enters a certain radius. So, well, this is also what friends say to me when I tell them what I'm working on. They say, that's easy, I can do that too. It's just a black screen, it's easy. So this is the first picture you send home. And then slowly your new cruiser gets swallowed up by the black hole, and you decide to take a second picture. This time you aim it right at where you think the red moon is. Then what you actually see is this. So here you still see the black hole, the horizon of the black hole. On top of that, you see some squashed, weird, gray, moon-like object. And then way above it, you see the red moon. So this is actually really weird to you. You've expected to see the red moon there, and the gray moon is in your back. You shouldn't see this one at all, right? That's what your intuition tells you. But what actually happens, if you trace the light rays from this gray moon behind you, they go below the black hole, they get curved all the way up into your camera. And for the red moon, the rays that go straight towards you, they actually get swallowed up, curved into the black hole. You don't see them. But the rays going up from the red moon, they get curved back down into your camera. So this is a render I made in Blender. And I decided to make this render last week, which is a really bad decision, to have a week before your presentation and then completely rewrite your code to be able to have the camera super close to the black hole, very strong curvature, your whole integration goes wrong. But I got something reasonably decent out of this. So then, let's see, your cruiser is completely gone. You are actually partway over the horizon as well. And as your last gift to your family back home, you make one picture, you aim your GoPro right up while you fall down, and what you see is this. So, sorry, it should be rotated, but the point will come across. So you're looking straight up, these moons are in the plane around you, and somehow they end up in your field of view. So what is actually happening in the very strong curvature of a black hole is that the light rays actually as a sort of a fountain. So for example, from the moon on this side, light rays going up, they get curved all the way back to you falling into the black hole. So in this case, it depends a bit on the field of view and some parameters. You can almost see the whole sky around the black hole in one image. Okay, so that was the introduction. Now let me properly start the presentation by at least mentioning my name. So my name is Ben de Vries. I'm an astrophysicist and I work as a scientific visualization advisor at SURF. And SURF is a Dutch organization for research and education in the Netherlands. So for example, we have a supercomputer that researchers can use to do their scientific calculations, and we do many other things. So why would you want to render things in spacetime? Maybe a few of you have seen the image a couple of years ago. This is actually the first image that we've been able to make of a black hole, of the surrounding of a black hole. So we're actually coming into the era that we can resolve these objects and we can resolve the stuff around it and we can start to see the curvature that these black holes have on the light that comes from stuff very close by. So making images of black holes is also scientifically relevant. And of course, it's just a lot of fun. And maybe some of you have seen the movie in 2015. I have to mention them, of course. This is the movie Interstellar. It's been made, well, the initiative of the movie even comes from a Nobel Prize winner in physics, Kip Thorne. And they, for the first time, made this really awesome picture of an animation of a black hole, what it would look like when you're close by. So it's also really cool, and it's a really nice way to communicate science and physics to the general public as well. So I wanted to make such a render engine in Blender, and for this I needed a couple of things. I really wanted it to be scientifically correct, so the effects I built into it, I wanted them to be based on peer-reviewed, published scientific techniques. I wanted to be able to put both the camera and objects close by and far away. For example, for many astronomical things, it's interesting to put the camera far away because we are far away. And then study things that are either close or far away from the black hole. But if you want to make some cool images, you want the camera to be close to the black hole and see what things look like. And furthermore, I wanted it to be available to everybody, to be able to, for everybody to go and try and make a render of a black hole or any type of curved space-time. But of course, like always, there's one problem. And the big problem in this case is that light doesn't travel in straight lines anymore. So that was what I wanted to convey in the example at the beginning. Things get really complicated and really confusing. But furthermore, if you want to implement the fact that light doesn't travel in straight lines anymore in Blender, you have to go into the render engine and build in the physics in the render engine. Now I put a big 1 here. Maybe a bit strange, but anyways, I've talked about light rays being bent in a gravitational field. So first we have to talk about why does gravity affect the light? Then I have to give a bit of a disclaimer. I promised not to use any equations when I proposed this talk. So I've tried to put this in a way that's understandable for everybody pursuing different things in life. But if you happen to be some mathematician or some physicist, You might cringe a little bit here and there. You might feel the urge to put up your hand because things are much more complicated. So for you guys, I wanna give a disclaimer. Well, if you talk about gravity, if you talk about the theory of gravity, you have to talk about this guy, you have to talk about Einstein. In the beginning of the last century, he was really thinking deeply about the fact, which was already known for a couple of hundred of years, that gravitation affects the movement of all bodies, independent of any of the properties of these bodies. So if you think about this really hard, you would think like, okay, if I throw a feather and if I throw a bowling ball, that stuff moves differently. You know, your intuition says that that's quite different. And I'm telling you that it's not. What's up? Well, of course, air resistance is up. And that's a very easy thing to say right now. But humanity has taken over 2,000 years to really peel away all the layers that makes things move here on the Earth. But to convince you that this is true, I have taken a clip from a BBC documentary, which may be a bad idea, I don't know. But it's just awesome. I can look this and look at it all the time because it's really strange, but it's movement at its most fundamental. So it's together with Brian Cox. It's highly advised to look at this documentary. So what we have here, we have a bowling ball and a feather that are hung to the ceiling of a very large vacuum chamber. So it's an extremely large vacuum chamber. And they're dropped down, and then you can truly see that these things falling in gravity, it doesn't matter if it's a feather, a bowling ball, if it's the moon, it doesn't matter, they fall the same way. Well, and then Einstein is the kind of person that always takes it the next step. So he thinks like, okay, if all massive bodies are to be treated equally in a gravitational field, then I'm going to treat light equally as well. And that's the step he made. And he made a really big, large theory about this. And of course, as a physicist, he wanted to make predictions to test his theory. So he came up with one of these tests to see if you could actually see a star behind the disk of the sun. So you have the sun in the sky, and when a star moves behind the disk of the sun will block sight of this star. But in Einstein's theory, he actually had the hypothesis that you could see the star just behind the disk as well. Why? Because light gets bent around the sun towards the Earth. So a big expedition was set up by Dyson and Eddington. And of course, you need like a solar eclipse to block out the star or the sun, because otherwise you won't see anything. You have to have these specific stars that you need to observe. So they went out and they did this. And then in 1919, they made the headlines, and Einstein's theory triumphed and was at least partly settled to be the new theory for gravity. And very deeply in the theory of gravitation that Einstein proposed is that gravity is no force anymore. Gravity is actually the curvature of space-time. Now, to make any sense of this, let's leave four-dimensional space-time and let's look at a case that's a little bit more familiar to us and that we can actually visualize. So let's take the surface of the Earth. Let's take this as a two-dimensional surface, so no jumping, no mountains, no funny business, just a two-dimensional surface. And we know that if we look at the map of this two-dimensional surface, stuff is up. There's something weird. If you have the map of the Earth, you cannot just take a ruler, put this on there, and measure a distance. This doesn't work. In this case, I have taken an equirectangular projection of the surface of this two-dimensional sphere onto a flat piece of paper. And measuring the distances between 2 points on the Earth, you need to do something special. You cannot just measure them directly. Even though one axis you might be able to measure in this projection, the other ruler actually changes depending on where you are on the Earth. This is because the sphere of the Earth is curved. But there's something you can do. If you take a little patch of the Earth, let's say some city or something, and you make a map of this, then things are okay. Then you can take your rulers, and in this small map of this city, you can measure distances just fine. As long as it's so-called local, you can do this. So this type of curvature that you have here is locally flat, but globally it is curved. And this is exactly the same as what you have in four-dimensional spacetime in Einstein's theory. But then is the question, how can I measure these distances? Well, the way you do this is you take many of these small little patches, and in one of these patches, you measure the distance of or you draw a straight line. Then you take another patch, you draw another straight line, another patch, etc. And then you glue these all together, and then you get a global curve, which is actually the best thing you can do to make a straight line in curved space. And this is called a geodesic. And the funny thing is, if you then take two people at the equator of the Earth, both moving upwards towards the pole, so they start out with a parallel direction, but they end up crossing each other at the North Pole. And this is very typical when you know that you are in a curved space. When you start out parallel, you might end up crossing other parallel lines to you. In a flat space, you don't have this. If two lines are parallel, they'll be parallel everywhere. Okay, so gravity works quite the same, but then in 4 dimensions, and with some complications that you have 3 spatial dimensions and 1 time dimension, but we'll leave that for now. So also here, if you want to study the movement of particles, Einstein says you have to look at straight lines. If there are no forces acting on the particle will follow a straight line, but then generalized to a geodesic. So if you have a little bit of physics education, this sounds very familiar. It sounds the same as what Newton said, but then in flat space. If there are no forces acting on a body, it stays at constant velocity or it stays standing still, and it moves in a straight line. So this is the same, but then generalized to a geodesic. And then the whole other part of the theory is that there is a coupling. So you have stuff that's in a space, that's curved. How stuff moves depends on how the stuff is curved. But how the stuff is curved depends on what's in there. So this makes the theory really quite difficult. So you have masses in your spacetime that determine the curvature of this spacetime. And how these masses move in spacetime depends on how it's curved. So this is very much coupled. But I will not go into that too deeply. And then, my apologies, this is one slide with equations, just for the couple of people who like that, if there are any. This is the equation for a geodesic. This might look like whatever, but this is actually very similar to one of the equations of Newton, namely that the mass times acceleration is the net force acting on a body, but then when there are no forces. So if you break this down, on the left in the red, you have the second derivative of the position. This is the acceleration. Then in the middle, you have something nasty. And then on the right, you have 0. This means no forces act on the body. So this thing here, with the capital gamma and all the stuff, this is actually the curvature. And here you see that if you forget the curvature, you just get the equation of Newton back. Namely, the acceleration is 0, the velocity is constant, it moves in a straight line. So for the people that had some Newton, some physics, this might sound familiar. And then, of course, there's more nasty stuff in the curvature of spacetime. And so this big gamma is given by some derivatives, forget about it. And then you have this matrix, and this matrix actually gives you distances in your curved space. So this is a little bit like the theorem of Pythagoras, right? So that's a little bit how one part of the theory of Einstein is constructed. So this is the movement part. I will not talk about how spacetime is curved by mass. That's outside the scope of even 50 minutes. So, and then you can take your SciPy, and I'm a big fan of SymPy as well, to go and solve these differential equations. There are actually four. It's four-dimensional spacetime. Well, you can get rid of one if you decide to look at photons. These are coupled differential equations, and you can solve them for an initial condition. So if you take a location and a direction in which you want to send your photon, you can solve these equations numerically. Sorry, so these renders, these images are actually real renders. I'm really happy that I was able to get them in time. But let's look at some other examples and how this works in Blender. So it's actually ridiculously simple what I've set up. It's a camera and it's a sphere. That's all. That's the whole Blender scene. And this sphere actually represents the part of the space that is curved. So outside this sphere, so inside the sphere, I use a custom render engine to track how light rays move through the space. And outside, I simply use the basic ray tracing that's already implemented in Blender, so light rays travel in straight lines. And then the last component is a nice sky image, for example, some Hubble image that I've put in. Yes, this is a note to self. This sphere is the region where spacetime is curved. So the black hole is actually much smaller. You can set the size of the black hole how you want. In all the things I show, the black hole is about 1/60th of the size of this sphere. And then if you make a render using this, you get this swirling kind of image. Well, in the center, you have the black hole. And another thing that's directly very clear is this large ring. This is called the Einstein ring. And inside, things seem to be smeared out spherically. And outside, it seems to be a little bit less. Is this visible with the lights? It's good? Okay. So let's have a look at what light rays do. So let's take a slice of this sphere, and let's look at how light rays travel in this slice. So you send them all in this direction through the sphere, and you see that the ones furthest away from the black hole get curved the least. And the closer the light rays come to the black hole, the stronger they are deviated from straight lines. And you see that in this plot, the ones that come close, they even get deflected all the way down. And then if you look at this very high quality picture of light rays even closer, you see that they can even be completely deflected back at you. So photons coming from your face can be deflected around the black hole, returning to you. They can even make a couple of round trips around the black hole before they get ejected or swallowed up. So to understand this image a little bit better, the photons, the pixels really close to the black hole, these are really strongly curved. These are photons that can even come from the back of the camera. They can come from, they can make multiple round trips before they end up in the camera. And this is the strongest curved stuff. Then much of what is in between the Einstein ring and the black hole, these can actually come from all sides around. So if you have a light ray coming from the camera, it goes over the top of the black hole, it goes all the way down. and the one going under the black hole is deviated all the way upwards. So stuff you see here is actually above the camera. Then you get the Einstein ring, and this is very strongly lensed light that comes from an object directly behind the black hole. So if you have a star directly behind the black hole, it will get imaged, projected into this Einstein ring. And the stuff outside, it is the very moderately deflected light rays. And then you can also set this in motion. So the animation you're going to see is just animating this sphere going up and down. And then it looks like this. So then you see the Einstein ring changing when the black hole moves. That's because when the black hole moves, the stuff behind it changes too. And then if you look at the stuff inside the Einstein ring and outside the Einstein ring, it has an apparent motion in opposite directions. Thanks. Yeah, well, I was pretty excited when it came out. It's true. I have to admit it, yeah. So without getting into it too much, you see stuff inside moving that direction when stuff outside the Einstein ring moves the other direction. That's because the stuff inside the Einstein reflection, inside the Einstein ring is also inverted.
Are questions allowed?
Yeah.
All right. So if we see some stuff that's curved, can we tell the position of this stuff based on some parameters of the black hole?
If you know what the black hole looks like, then you can one-to-one map where the stuff comes from.
So there is some equation to that?
Yeah, there is. Yeah. If you know exactly how space-time is curved around the black hole, so you know how massive it is in its rotation and stuff, then you can directly link that.
So we need to know the strength
of the curvature. Yeah. And this is actually a technique in astronomy that's used a lot, and because this. Also, in the Einstein ring especially, the light is very much focused. So you receive much more photons from the object than you would get when there's no black hole present. So you can actually look at things further away because the black hole magnifies it. And then you want to know some stuff about the black hole, how far away it is, etc. Then you can reconstruct things as well, if you're lucky. Okay, yeah, because, well, within the Einstein ring, the curvature is such that just 1 second. If light rays go over, but slightly to the right, they get curved to the side on the left. And light rays that go to the left, top side left of the black hole, they get curved to the right below. So there's a flip. And that's why things move in different directions inside and outside the Einstein ring. Yeah, so, just the same thing again, because, whatever, it's cool. All right, let's see, I'm like half an hour in, so I have some time left. So let's look at some things close by. So what you just saw was like a sky image lensed by the black hole, so this stuff is like very far away. But now, because it's Blender, we have to put in a Suzanne. That's what we have to do, so that's what I did. And then you can make it move. And so at this point of the image, Suzanne is behind the black hole to the left. And at the other end of the animation, Suzanne is exactly behind the black hole. And you see Suzanne kind of forming an Einstein ring. So this is the first image. So this is the camera directly aimed at the sphere. And Suzanne is to the left behind the sphere. And in this case, you see that you have two images of Suzanne. And like I talked about with the previous image, the image inside the Einstein ring is flipped, and the one outside is kind of normal. And you have these two images of Suzanne because you have two lines of sight towards the same object. So here, if you again take a slice through the curved spacetime, the rays above the black hole form a primary image of Suzanne, but the rays below, at the other side of the black hole, they can come to the same object and form a secondary image. And that's what you see here. It's the same object, but two lines of sight that end up at this object. And then here, it's a headshot. It's an Einstein ring of Suzanne. And because Suzanne is exactly behind the black hole, she gets smeared out in this ring around. And then as a last example, because of the Interstellar movie and everything, I have to put in a disk. I have to see what that looks like. So this is no curvature. So it's just a flat disk. It's it is really thin. It has no dimensions in height. And I just put on a Photoshop cloud image because, well, why not? And then if you look at this in curved space, you get this maybe now familiar image of a black hole. So of a disk around a black hole. So there are a few things to mention here. You see the extrusion above the black hole. What you're actually, oh, I forgot your question. Well, maybe at the end, right? Or
it's related to what you had right before.
Yeah,
As you wish.
we'll do it at the end. Sorry. And so the extrusion at the top, what you're actually seeing, you're seeing the disk behind the black hole and then the top side. So the light rays that go over the black hole get curved downwards and they end up at the disk at the top side of the disk. Similarly, the extrusion below is the same, but the other way around. You have light rays going below the black hole, and they get curved upwards. So there you see the disk behind the black hole, but then the underside of the disk. And then there's one other feature, and I had to use quite some multi-sampling. Well, it's like 10. It's not a lot, of course, but it's computationally heavy. So to resolve at least a little bit this very thin ring, a circular ring around the black hole. Some people call this the ring of fire. There are some different names for it. But these are photons that actually make multiple round trips around the black hole before ending up in your camera. So light ray comes from the disk. It's caught in this not quite stable orbit around the black hole. And at some point, it has a deviation. It either falls in, it goes somewhere else, or it ends up in your camera. So this is a really thin line. Yeah, this is a picture of what the light rays do that I just explained. So if you go above the black hole, you end up behind the black hole, the disk behind and the top side. If you go below, you get the disk behind the black hole, but the underside. Well, and then let's have a look at what the disk looks like at different viewing angles. It's not quite the quality I wanted it to be, but you can really nicely see that the apparent shape of the disk is very different depending on how you view it. So if you view it almost edge-on, you get this classical, well, not classical, this interstellar-like image of the disk. But if you look at it from above, it becomes more and more like the spherical, symmetric disk that you put in the first place. But the Einstein ring actually, or the Einstein ring, the ring of fire actually stays there no matter how you look at it. Yeah.
If we look at the picture from the Event Horizon Telescope, which angle should it be?
Yeah. If you try to be practical, it always gets a lot more difficult. That's a problem. You have disks in astronomy a lot. And you always have the problem that you have no idea at what angle you're looking at them. And it can be really difficult to determine the orientation of the system compared to you. So this is often like an error bar if they try to analyze this and they don't know this. Yeah, it's called the inclination. And So also, I don't think they know this inclination for the black hole that they've imaged. But maybe they've done other measurements in the last in the last year or so. But I don't know. But that is something that needs to go into your analysis, and that's often really tricky. Stuff is far away. Okay, so then I would like to start and summarize my talk. So we've seen a couple of images. So we have been standing on the horizon of a black hole. We've been kind of looking around, and we have seen that stuff looks really weird. And please, black holes do not have colored moon-like objects. I have put these in because otherwise you have no idea what's going on. Light's going all over the place. If you have just a sky map of stars, you have no idea what you're looking at. So I put in some weird moons to just give you an orientation of where the light rays are going. And then we looked at stuff very far away from the black hole, so the background, the starry background, how this was lensed by the black hole. We have done some Blender objects. You can put in any object you want. If you want, you can put the black hole in your living room and see what it looks like. If that's of interest to you, you're lucky that the actual gravitation is not present in your living room, I guess, but still. And then, of course, you can put in specialized geometries that you're interested in from whatever point of view that you have. So it's really nice. I made some crazy images from some crazy physics, and it's nice to look at. It's a start of a render engine in Blender that I hope everybody can use who's interested. And it's based on the real theory. There are no shortcuts, no tricks, no funny business. And you can put the camera close by, far away. You can put stuff close by and far away from the black hole and see what it looks like. Then, of course, there are many plans. One of the downsides is that it's computationally very heavy. So I'm working on different ways to speed this up. I also want to make some proper code of it. It's a nice little hacked thing, especially the render engine. The calculations are pretty okay, but that needs to be improved. Then there are actually only kind of two flavors of black holes. Black holes don't have that many parameters. They have their mass, and they have like a rotation and maybe a charge. And well, there's one other type of black hole that I want to implement as well. And then see if I can publish this somewhere, at least get people to know this exists. So what's not in it is actually the redshift. So light that actually goes out of a gravitational field gets redshifted, so it changes its color. That's not in there. Then collisions inside this sphere are not in there yet. I'm close. So the sphere represents the space where I treat the space as curved. And the polarization of light. So light is an oscillation, and it can oscillate in different directions. This also gets influenced by the curvature. So this is also something that's not in the code right now. Then, of course, I have to thank all the people that are behind all these things that I've been able to use freely. So Blender, SymPy, SciPy, Python. It's just really awesome that people make these things and that you can just use them. And I want this to be the same. And there are also some papers. So this first paper I've used a lot. It's the paper published by the people behind Interstellar. So they scientifically published what they've done for the movie. And some people from the Radboud University that wrote some really nice papers that I used a lot. So if you want to know more, come and talk to me. If you like, you can go to the GitHub repo. I write some blogs every now and then. If you want to see more of this, scan the code. And I would like to thank you for your attention. And if there are questions, please let me know. There's at least one question, and that's you, right? Yeah.
Do I need a mic for the recording? Or?
Well, you can take this one.
Yeah.
Thank you. Well, thanks a lot for the talk. Really cool stuff. My question was about the spiraling light rays. You mentioned that you get two images, but does the spiral mean that you actually get infinitely many copies of the space as you get closer and closer to the black hole itself? And do you have that, like, so the first question, which seems to be yes, is does that happen in real life? And the second question is do you have that in the renderer as well?
Yeah, so it's you have the possibility for many more images. You're right. In most cases, you won't be able to see them because you cannot resolve them. Your resolution is not high enough to actually see them. So no, I don't see more than two images in my code. I would really need to zoom in on this part close to the horizon to see the other ones pop up. And the other question is about, are there infinite images in real life? Well, that's a very big question. Does infinity exist in real life? I don't think I have the time to talk about this. But probably, yeah, at some point, if you approach infinity, your scale will become really small. And then we need some other theory in physics to probably talk about that. But yeah, it's a difficult, it's a big topic. Yeah.
Thank you.
Yeah. The one behind you was just first.
Thanks for the talk. In terms of the actual ray tracing, is there, this might be a silly question, but like, is there any issues with the asymmetry in the sense that like you're tracing the wrong way, right? Like the light's coming from the object to the camera, and you're tracing from the camera to the object. Do any, like maybe the redshift and stuff like that, do any of those pose any sort of weird asymmetries in like reversing that, which you obviously don't get in straight lines?
Yeah, you guys have good questions, man. That's a really good question. So actually, when you render, you trace photons from the camera to the object. So that's the other way around as the physical world works. So yeah, you need to think about, is it symmetric? And in this case, is it symmetric in time or in the parameter that you use for this trajectory? And in the case of a Schwarzschild black hole, this would be a perfectly spherical black hole. This is all fine. If you have a black hole with rotation, then you need to think about this, because if you trace it the other way around, you treat the black hole as rotating the other direction. So you need to keep that in mind. Yeah, very good question. Then you, yeah.
Gleb Alexandrov did a few years ago a video tutorial about creating a black hole in Blender that was mainly depending on the refraction material. So if you have watched that, is it only a mimicking the black hole, or is it like a good representation of it?
Yeah, so first of all, his stuff is really, looks really good. I'm quite jealous. But yeah, it is of course an approximation. And I wanted to start as general as possible. So really just tracing these photons really as the physics tells you. And this is especially for cases when you start to get close to the black hole. Then you will have deviations from this. But also if you wanted to treat other curvatures, for example, this rotating black hole that I just talked about, then these symmetries, like perfectly spherically symmetric black hole has a lot of symmetry, which you can use. If it rotates, you break one of these symmetry axes, and you need to make it more general. So his stuff this is a really good approximation, and you get really good images. Now I don't have it in mind very, very well, but for example, things like the Ring of Fire, I don't know if he gets that out, and how he does that, I don't remember, for example. But yeah, it's a good approximation. Yeah.
Hello. if you shine a light from the point of view of the camera and you have an object behind the black hole, would your spherical curved space-time would cast rays after that in the direction they should have been curved?
Yeah. So I had to make some choices there. So of course, if you have a light ray and it bounces off some object in curved space, how do you treat the bounced light ray? And so I worked out the render engine in two ways, because this is actually what I'm working on, because it's really computationally really tough. So the one I showed now is that you only have curved space inside this sphere. And inside this sphere, I do no collisions. Outside this sphere, I do, but then I just use Blender's collision detection in flat space. Then to make the images at the start of the presentation, I actually need the camera to go inside this sphere to actually go onto the horizon of the black hole. So I had to reprogram this last week to get rid of this scheme and just have curved space everywhere. And then I left collisions out. And that's something to build in later. But the code is so that you just give it a position and a direction, and it calculates the trajectory. So if that then collides with an object, you have another position, and you determine the new direction based on the properties of this object that it collides with, and then you call the algorithm again, using that as a starting condition. Yeah, so in the first version of my render engine, it did. And now in the second version, I've got both online. All space is curved. So, but then you have no collisions yet. Yeah.
So it's a bit of a question about the inherent flexibility. And so do you integrate sort of the whole spectrum differently? Because you can get some dispersive-like effects where the different parts of the spectrum are doing different things, and some very, very intricate color things happen when you do that.
Yeah, so put on the thumbing screw, you call it in Dutch. It's like this torture, medieval torture thing that they put on your thumb to actually crush it. No light, no color, and no, because in local space, in flat space, you would actually need to properly treat the Maxwell equations, so the equations for electromagnetic fields, and then you get like diffraction and whatever kind of complicated stuff. That's all not in there. Yeah. Disappointing, but it will come.
Hello. Thanks for the talk, but you keep mentioning that it's like very computationally expensive. So when you like render images out, do you like just hard limit the amount of passes, or like is it like, oh, if light approaches these many like bounces or like stuff like that, and the render engine is just like, no, not anymore?
Yeah, so that was stupid of me to mention, I guess. There are a couple of things in your question. One is about the bounces and the collisions, I think. So in the second version of the render engine, I haven't fixed that. I haven't figured that out yet, so where everything is curved everywhere. In the other one, I only do collisions outside the piece that is curved spacetime. So there it's just the Blender stuff. And then the second question might be about multi-sampling and stuff. How many passes you do? Very, very little. Often like one. So one photon per pixel. The images you saw at the beginning are one photon per pixel. And that, you've probably seen the rigid sides of the moons and stuff. And for example, for the disk to nicely or more nicely get this ring of fire, I upped it to 5 or 10 passes for the multi-sample. This is really, really low. It takes about a thousandth of a second to do one photon. So then take the resolution, do the multiplying. Yeah, it goes up really quick, and this is a big problem for me to iterate on. So mostly I make like images that are 124 by 124 to see if it makes any sense, and then before I do anything bigger, because otherwise I cannot iterate in a. But yeah, so that's something I need to work on. Yeah. Yep, and then you.
I just wanted to ask about your render. Did you implemented some sort of curved BVH to accelerate some structure to solve it faster? And my other question is, the race currently is like, is it a bidirectional path tracing like cycles, for example, that solves the race as it was infinitely fast photons? Or could you, for example, as you mentioned, you have also the fourth dimension matrix, the time, could you fix the photon in speed on, for example, solve the Suzanne moving with a different light speed, for example, if it goes through the black hole or if it goes directly to the camera, and, for example, solve the tachyon entering in field of view, would it work also in your render, or is it something?
How many questions in one? I couldn't quite 100% follow, but variable light speed, no. Einstein doesn't like it, me neither. It's a fixed, yeah, fixed.
The fixed one may also solve faster in some areas.
Yeah, and then that question, yeah, I have used some tricks to speed it up. So for a spherically black hole, you only need to calculate the rays in one slice, and then you can rotate it and change it to get all the other rays, because it's totally spherically symmetric. So I make a grid of a line from the center to far away. I calculate all the trajectories of the photon, and then I use that to calculate whatever direction the photon may have.
But if you have a tachyon that enters the field of view, will it also in 10 space?
Oh, there are no tachyons, but we can continue this this after if you like. Yeah. And then you.
Hello, nice work. For visualization, did you think about 360 video? Is video possible? How long does it take for making that one picture with the 4 moons? And then maybe last, for seeing if I understand it well, if you're standing on the horizon and look up and there should be a moon, is the moon in one dot? Is it condensed?
Yeah, so your first question is about kind of real time doing things or making a 360 video. Real time at this point is outside my scope, but yeah, who knows eventually if we can speed it up even more. And for that picture, yeah, so there is no moon on the above your head. If there would be a moon above your head, it would be stretched out. Because if you go take light rays from the camera up, they would diverge. Sorry, yeah, they would, yeah. So the moon would diverge, and because yeah, exactly, yeah.
How long does the time take for the picture?
Which one? The 4 moons. Yeah, that took like 2 days. Yeah, it's nasty.
Is the renderer written in Python?
Yes, it is.
Okay.
Yeah, it's based on it's using Python, and it's using NumPy, SymPy, SciPy, which on the back end uses C. Yeah.
Very general. Okay, so you showed the image of event horizon, and that's an image produced from observational data, let's say. Is the algorithms they tested and verified, is that a render engine? Is there something overlapping between these two? Your image and the...
Yeah, so I use the same techniques as they use. I use the paper. Yeah, I use the physics, and they also use a integrator to integrate the trajectory of photons in that way. And then if you do things from far away and you have like dust clouds and things, you would need to do proper radiative transfer and that kind of stuff. That's not yet what I'm doing.
Okay.
Yeah.
It's just because they had a telescope.
Yeah.
And you have
There are many different kind of codes. You see some codes popping up and leaving, improving. And I've taken papers that's like 1 year old, taking their techniques, implemented them in Blender, so to say. Yeah.
And then for the publishing, there's a journal, JOSS, Journal of Open Source Software.
Okay, well,
For scientists
yeah.
to produce code.
Yeah, that's a very good tip. Thanks. Yeah, excellent. Okay, let's have one more question, and then you guys who are still left should go for lunch.
This is weird. I'm sorry. I'm not used to using a microphone. I wanted to ask a question. How well does the ray tracer scale to, for example, having multiple black holes or black holes of weird shapes, like a donut, for example?
Yeah, that would be really interesting. If you remember the slide with the equations, and you saw the matrix in there, that's called the metric. That determines what distances are in space-time and how that changes over globally. If you wanted to have two black holes, you have to encode it in this metric. So the mass distribution is encoded in this metric. So so that's the whole other part that I skipped in this talk. So on the one hand, you have stuff moving in space-time. So the curvature of space-time is fixed and stuff moves in it. That's one part of the theory. Then the other part of the theory is how mass, or energy and momentum, curve space-time. And those two are coupled. So there you could put in anything you want. You could put in some mass energy distribution, multiple black holes and blah, blah, blah. And then you have a really difficult calculation, but it's possible to then calculate what this metric would look like. And then you can do the movement in the case of, for example, two black holes moving, orbiting each other, for example, or a donut or a piece of cake of whatever you like. And so that's like the other part of the calculations where you could do this. And I'm only doing the movement in curved spacetime. I am not yet, well, I'm not doing the calculation of the curvature based on the mass distribution.
Okay, I guess this is a more technical question. With the metric, how easy is it to derive the metric for the two sphere case?
Okay, we'll take this offline. That's a really good question, and there are very, very nice methods to do this, but it gets a bit involved, I guess. So if nobody else has any questions, I'll be around here for a little bit, and you can ask me.